Okay, so in the last video, we obtained this result that the closed integral of Jn over the uh, area is equal to 0. That means the normal component of the current density over the chosen area, whatever we have, that is going to be 0. So this is a result that we obtained in the last class. And now we have to see when, at what condition this will be obtained. Okay, so the area that we have chosen is actually we have taken a cubical structure of length L. Okay. Okay. In this case, uh, you can have closed integral j and dA equal to 0 when it is possible in two ways. One is psi tends to 0 at the boundaries. If the wave function, whatever we have, is 0 at the boundary, wherever the boundaries are, then you will get the closed integral j and dA equal to 0 because j is this quantity. If the wave function is 0 at the boundary, this going to be 0 at the boundary, and if you take it over the uh, closed boundary, all the values are going to be 0. It's going to be 0. So you will get this condition. But the special part of the wave function in this case is u of r. Okay, I'm not writing the entire part. I will just take the exponential part of it. We reach to I k dot r. This is a form of the wave function, and you can see that this wave function, you cannot make 0 at any of these boundaries. So whatever value you give, this is not going to 0. It's an increasing exponential, and so this is not the valid uh, condition that we want. And the another possibility here is that the wave function psi is periodic over the chosen boundary. If the wave function is periodic over this boundary, then again it will satisfy this condition. And this is actually, on this particular case, you can show it by taking the plane wave equation like this. You can take it this quantity as the equation, wave function, and you can use the j expression to find out j, and you just integrate it and see whether it is 0 or not. So this is uh, the another possibility that the periodic wave function has to be periodic. Okay, so if the wave function is periodic, then it has to repeat whatever value this is having at this moment. Suppose I have a maximum value, and if it is periodic, I can assure that this point after my periodicity interval, again I will be getting the similar value. Okay, so that is the condition that is given by my periodicity condition. So let me take the wave function as e raised to I k r. I'm writing it in the general form. So when the r increases by L, e raised to I k r plus L, again you will be having the same value, whatever value it is. There is no restriction for that. It can take any value, can be plus anything, minus anything, 0 or whatever. Only thing is that both value has to be the same. So same is the case. Suppose this is x-axis in this direction, and same is the case with y-axis, same is the case with z-axis, like that. Okay. So if that is the case, then you already obtain. You can see when this happened. You know that 2 and pi. If you put here, there is no change for the quantity. So this is going to be the KL here. KL is going to be 2n pi, where n can take values like 0, plus or minus 1, plus or minus 2, etc. like that. So by this plus or minus 1 here, earlier we have seen only plus 1 general. Here this is like okay, after this boundary, this is whatever is coming here, it's going to repeat, and again it will be forming something like this. Okay, same we can go in the other direction also, negative direction also. So depending upon that, you can take plus and minus or whatever on all the axes. So this is a general picture. You can have the restrictions in x, y, z separately. So that is going to be k set L equal to 2nx by ky L equal to 2ny by k set L equal to 2nz by, where nx, ny, nz all can take all these possible values, plus 0, plus 1, plus or minus 1, whatever. Okay, so now we got the condensation condition here, and another, our aim here is to actually count the number of states between two energy interval. So for that, first we develop the condensation condition, and now we have to count the energy between E and E plus D. Okay, to calculate the energy between E and E plus D, first let us draw the possible values of N and arrange them into a kind of a spatial structure, and this is called N space. And here we are taking the possible values of nx, ny, nz, like that. So all the values of n is not permitted for us according to the condensation rule. There is only some values which are permitted, which corresponds to n1, 2, 3, 4, etc., 5, etc., 1, 2, 3, 4, like that. So in a two dimension, if you draw, this will give an array of points like this. These are the permitted, these points are the permitted values of n, or values of nx and nz. Same way you can draw it in the y direction, so that it will become like a spatial distribution of points, and each of these points corresponds to a particular state, right? A particular energy state. Okay, now what I'm going to do is I'm just connecting the nearby points, and in the two dimension it looks like a square, and in three dimension if you connect it, you can form a cube, and each of these cube contain 8 number of such kind of possible points, and each of these points are actually connected with the 8 such kind of cubes. So in a sense, the contribution of one point to the cube is actually 1 by 8 into 8, that is nothing but 1. So each cube in this number space corresponds to a particular energy state. Now if you want to calculate the number of energy between E and E plus D, what we have to do is we just have to find out the n corresponding to E, and yeah, corresponding n we have to find out corresponding. Here there will be an additional number coming, so this is n plus dn corresponding to E plus D. So that is going to be something like this. So this is going to be the n, and this is going to be the n dn. Additional term is nothing but dn. Okay. So n is nothing but a general vector in this n space, and what we have corresponding to E, if you want to find out the number of possible state, what we supposed to do is we just have to find out what are the or how many number of such kind of cubes are there if you construct a volume with a radius n, like a spherical structure I can draw here by using n as a radius and dn as the thickness of it. So the number of cubes inside this structure will give you how many number of energy levels are the between these energy levels. Okay, so this actually you can do it straightforward manner. You know the radius and you can find out the surface area of that by using 4 pi n square expression, and we have a thickness here. It will give you 4 pi n square dn. And if you want to convert this into K space, you can just substitute the condensation condition here for the n square, or otherwise you can construct a separate space corresponding to an n space for each point here. If you draw an kx, ky, kz, you can have corresponding k points. So just like this array, we have a an array of points in K space, and that also form a spherical distribution, something like this. And similar way you can find it out, but instead of doing that, we can directly put from this condensation rule and find out the number of states in K space. So this is going to be something like 4 pi. Instead of n square, I can substitute KL 4 pi KL divided by 2 pi whole square into dn, that will become dk, and you will be having an L by 2 pi coming there. Okay, so this is going to be the number of states in the K space. So I'll call this as rho of k dk. Okay, but we know there is a one-to-one correspondence between k and d. So rho of e d is nothing but rho of k dk. So our aim is to find out rho of e, and for doing that, okay, this quantity I already obtained. This is going to be 4 pi k. Yeah, this I'll modify this expression a little bit. I can take L by 2 pi cube and k square dk. So that is going to be rho of ed, but rho of ed I can modify because e is nothing but p square by 2m, that is h cross square k square by 2m, or de is equal to 2k h cross square by 2m into dk. 2 will cancel, k h cross square by m. So this is k h cross square by m dk, and you have dk on both sides, you can cancel it, and m will come here, nothing else. 1k will cancel here. So this is going to be 4 pi L by 2 pi whole cube k, and of course m by h cross square, and this is your rho of e. That is a density of states with energy e. Okay, now as we are discussing the scattering problem, we don't want to find out the density of state throughout the entire theta and phi. So what we actually have to do in the scattering thing is we want to find out how many number of particles are scattered through a particular theta phi angle, and we call that as d omega, or the solid angle. So instead of calculating it through the entire area, so this is actually an integrated value over the thetas and phi. That is the reason 4 pi comes here. Instead of that, we can just calculate this quantity over a d omega. If we do that, nothing, no modification, we can just substitute. Instead of this integrated quantity, we can substitute d omega as the area through which the particle is whatever scattered. Okay, so this is your rho of E finally, L by 4 pi whole cube k m by h cross square. So this is something, okay, d omega. So rho of E we wanted to find out and we obtained it now, and now we can directly substitute this into our W equation. So that is WIF is equal to 2 pi by h cross into this quantity that we obtained and rho of E. Okay, just substitute. WIF equal to 2 pi by h cross. Then we have VIF, that is 1 by L cube, sorry, integral. This is inside that our potential, whatever it is, P of r prime e raised to I k dot r d v over some volume. This is elemental volume, okay, don't confuse it with potential. And square of that. Also, whatever we obtain now, rho of E, that is L by 4 pi whole cube k m by h cross square d omega. Here we have 1 by L cube square here, 1 L cube is there here, so this L cube will cancel, and numerator 2 pi k m, right? So I'll just combine and write 2 pi k m divided by 1 h cross here, h cross square here, that will become h cross cube. 4 pi cube is there down, so this is going to be 4 pi h cross, and all these things are having cube, and one L cube is also coming, L cube. So all these quantities cube, and yeah, h cross, and whatever remaining now, that is nothing but integral v of r e raised to I k r dv square of it into d omega. So this is your total transition rate, omega if. Okay, total transition rate through a solid angle d omega. One thing what we have to do now is to connect this with the scattering theory. So here we have transition rate between initial and final state. Okay, so in a scattering process, the final state is something like anything which changes from initial state is something which is scattered. So this refers some way to the number of particles which are scattered through a solid angle d omega. In okay, so the quantity d sigma by d omega differential cross section is something that we defined n by j. Yeah, so n is the number of particles which are scattered per unit time per unit solid angle. So this is actually the transition rate per unit time through this unit uh, through this solid angle. So if you divide it with d omega, it is nothing but our n. So this is like n is nothing but n that we define here is nothing but omega if divided by d omega per unit solid angle. Okay, so yeah, whatever remaining things you can substitute here instead of omega if. So that will be your n. And what about j? J is the incident intensity, and this you can calculate by using your you know the wave function already. You can find out the incident intensity, and that will be something like h cross k by m, and the square of the amplitude. And for this wave, the amplitude square is something like 1 by l, yeah, 1 by l cube root it is. So this is going to be 1 by l cube. That is the incident intensity that is divided with the this omega if divided by d omega, and that is going to be your diffraction cross section. Okay, so this is something that we have to calculate, and that is going to be, if you divide omega if with d omega, this is going to be nothing but the remaining terms, and these quantities which will come up, so that will become ml cube divided by h cross k 2 pi mk divided by 2 pi h cross l whole cube, and integral b of r e raised to I k r dv, or here if you want to change, you can just use d cube r if you're confusing with the dv. This is square of it, and that d omega already has gone. Okay, if we rearrange some of the terms a little bit, you will be able to produce the expression that you obtained when we are doing the scattering theory. And I will just write the expression directly: 1 by 4 pi 2m, nothing to do, just cancel the terms and rearrange it. That's all. 2m by h cross square integral e raised to I k r v of r dv whole square. And this is the expression that we obtained the scattering theory, and which we are able to reproduce by using time dependent perturbation theory.